Welcome, folks. Welcome to today's live broadcast, our free webinar, part of an ongoing series that Heather and I will be continuing. Today, we'll be discussing machine learning and SharePoint, and what can it do for me? Along the right-hand side of your screen, you should see a chat box, and you can use that to talk back to us during the presentation. And today's presentation will be going for about 2 hours. We'll end up right around 3 o'clock Central Time. Your questions throughout the session are, of course, appreciated. There's no need to hold anything until the end. At the right-hand side chat, you can type those questions in whenever you'd like. Now, as I said, today we'll be talking about machine learning and SharePoint. What can it do for me? Now, a lot of folks coming into sessions like this have a predisposed idea of what machine learning is, and what you can do with it. But many folks don't, and I want to spend some time today talking about, in general, what is machine learning? What is it all about? And that big question, what can it do for me? So what is machine learning? Well, that cheeky answer, of course, teaching a machine to learn. Ha ha, that's just the first awful joke of the 2-hour block we have. But really, when you hear that phrase, machine learning, and please feel free to let me know in the chat what you believe, what you've heard, but we're talking about what machine learning really is in a general sense. And I'm going to ask in advance, by the way, for the forgiveness of those of you that already have a great deal of experience with this particular topic. I'll be taking some poetic license over the next 2 hours in order to actually get through a topic in the next 2 hours that is otherwise one that takes years and years of study. So machine learning in general describes a program, an application, that has the ability to learn. Something that can predict an answer to a question. And you'll see that word appear a lot during this session. Question. It's an important aspect of actually making machine learning do something for you, and one that I'll underscore and underline as many times as possible until I sound like a broken record, and that is, you have to know what question you want to ask in order for any kind of computer program to give an answer that you hope will be useful, and most especially with machine learning, because in many cases you don't have a whole lot of visibility into what it is the machine is actually learning. It becomes a sort of black box that gives answers every now and then. And for those answers to make sense, you have to ask the right questions and know what to ask. But a machine learning application is one that gives a prediction, given a certain number of features that could factor into a possible answer. And by features, I mean a word maybe perhaps makes more sense, variables, individual pieces of data. For example, if you wanted to predict the proper sale price of a home in your neighborhood, you might use some data that already exists about all the other homes in your neighborhood. How many square feet they have, how many floors they have, how many bedrooms, how many bathrooms, how big is the backyard, what other amenities might be there on the property. And each of those individual components describing a home for sale is a feature. So a feature is one little piece of data about the overall record of data, if you will. One of the goals, one of the purposes of machine learning, just one of many different uses for machine learning, is to make a prediction based on those combinations of features. In some cases, you can give the computer information about predictions that have already been made. In other words, homes that have already sold and how much they have sold for. And its job is to figure out which of those different features was most relevant to the sale price. So another part of machine learning, another way that machine learning can be used, another description of machine learning is, well, all of them really kind of aligned to the answer of math, but we'll talk about statistics in particular. A common description or depiction of machine learning is the analysis of these statistics to find trends in the data that you have. Now, this can be useful if you don't have specific labels, specific answers that you already know. You just want to sort of get to know your data. And if you want to get to know your data, that means understanding trends. That means perhaps even getting classification information about that data. How would this information be clustered into different groups? Is there any way to cluster the information that is relevant to me? This could be helpful for classifying data in terms of topics, for example. The same kind of statistical analysis can also figure out if there are any elements of your data that lie outside the general accepted world of the rest of that data, those outliers or anomalies, which can be helpful for detecting fraud. It could be helpful for detecting a superstar in your employee ranks. And perhaps in the chat you can share with us what sorts of things you might find a statistical analysis, or maybe what you've even used statistical analysis to solve for you now. Now, machine learning is kind of a big topic, as you can tell. I mean, this is a very general description of what it is. So are there any different kinds of machine learning? Yes, great question. Thanks for asking. And the second bad joke of the day has come to pass. Okay, well, let's get into that a little bit more. Are there different kinds of machine learning? There are different kinds, and I'm going to talk about each of these in some form or another. The overall approaches that we can take to machine learning can generally be grouped into one of these different categories, and I'm going to give some specific examples of what these approaches are commonly used for and what they really mean. But I'm just going to summarize for now. Supervised learning, the first approach for machine learning, means that you already know the answer to a bunch of, you know the answer to the question that you're seeking, the question that you're asking, as that applies to the data that you already have. In other words, you have, for every home that's sold in your neighborhood, you know how much it's sold for, and you know all the other bits of data about it. So you're supervising the learning by telling the answer to your computer, by giving the program the answer to the question that you're asking for all the data you already know. Now that might seem, well, that doesn't seem very helpful. We might be thinking, well, it actually is deeply helpful. Computers can't really understand on their own. Programs can't understand on their own. When you're looking for an answer, a specific kind of answer, like how much should I sell my house for, it doesn't really know how to get there unless you give it examples of what other houses have sold for. That's the whole purpose of machine learning, is you have some data that's already been tagged with the answer. And if that answer is, as long as the answer is valid, as long as your data is good, well then, you can go pretty far with supervised learning, making predictions of future bits of data. Now, of course, the more data you have, and the more correct answers you have to go with it, the better the computer can learn. How about unsupervised learning? If supervised means you, the human being, are supervising the whole process to make sure the computer program that you've written is doing its job, how about unsupervised? No, well, that doesn't mean like the whole, if you put 1,000 monkeys in a room with typewriters, one of them will eventually produce the works of Shakespeare. That's not what unsupervised learning is about. It's not because these monkeys are unsupervised by a human that they eventually, that's just pure statistics there, and also not really true. Unsupervised learning means, what can the computer infer about all this information? What can your program figure out on its own? Now, it can't figure out specific answers to questions because you haven't really asked it one. The whole point of a supervised learning experience is you have a question that you want to ask, and you have the answer to that question for a bunch of existing data. With unsupervised learning, you're not quite sure, necessarily, of a specific question. Now, you might be, but it's more like you have a task to assign. You want it to do something for you to make your job a little easier, like classify information based on the topic that's being discussed. That would be an example of unsupervised learning, where a computer looks at all the possible different stories that have been posted on a site, or movie reviews, or every speech ever made by every political candidate ever, and have it try to figure out, are they grouped in any way? Is there anything similar between these bits of data? Is there anything wildly different about these bits of data? How can I possibly classify or group these things together? That's one example. Semi-supervised learning, occasionally you check in on the monkeys to see how they're doing with the whole Shakespeare project. No, that's not true either. Semi-supervised learning is a sort of a combination of supervised and unsupervised, as the name might suggest. The idea being that you give it the answer for some bits of that data. It can make a better prediction if you give it some information. Every computer program that has to predict something can predict better with better information. With semi-supervised learning, you've given it the right answer to a few of the examples to help it tune its own algorithms to figure out, okay, well, he said that this house sold for this much, so these things might be kind of important, but let me go on and figure out the rest of the stuff on my own and see if my functions that I come up with agree with what the human told me for some of the answers. And that's, again, a poetic license being taken there, simplification somewhat of what semi-supervised learning is, but it has applications that we'll discuss in just a little while. Reinforcement learning. This is a really interesting topic. Perhaps you've heard recently of computer programs being taught to play video games. Reinforcement learning. With reinforcement learning, the idea is that you have a goal that you want the program to reach, and it's a very Pavlovian experience, the whole process of what the computer learns to reach that goal. Remember Pavlov? Does the name Pavlov ring a bell? And there's number 3. Does the name Pavlov ring a bell? Of course it does, because he rang a bell every time just before he gave each dog a treat, right? And when he rang the bell later on, he found that the dog started salivating in expectation of the treat. And reinforcement learning, you might say, is what Pavlov was really doing with those dogs. And there's positive reinforcement and negative reinforcement. That's pretty much how it works with computer-based reinforcement learning. There was an example recently of a computer-based reinforcement learning system that learned how to play Pac-Man. Now, it didn't know what the rules of Pac-Man were. It didn't know who the ghosts were named after. It didn't know the score. It didn't even care, really, ultimately, until the game was over about what the score was. But what it did learn is that if Pac-Man was eaten by a ghost, that was a negative reinforcement. And if it ate a pellet, that was a small positive reinforcement. If it ate a power pellet, which allowed Pac-Man to go chasing after the ghosts, well, that was an even bigger reward to be used in reinforcement. But it didn't know that it can eat ghosts then. So it had to guess, it had to try, it had to experiment. This program had to experiment. All these different permutations. What happens if I eat a pellet and then eat a ghost? What happens if I happen to run into a ghost after I've eaten a power pellet? How about after my power pellet has expired, or the ghosts are starting to flash because my power pellet is going to expire soon? It wasn't told that these things happened. It just noticed that they were happening, and it noticed that it tended to die if it was going after a ghost and it wasn't Pac-Man wasn't under the influence of a power pellet. So it figured it out. Eventually, it actually figured it out. It figured out how to play Pac-Man. How did it know how well it was doing? Well, that's where the score came in. At the end of each round, it would look at the score. And then it'd go back over, like we overanalyzed the past in some situation that maybe we regret having been in, right? It went back over and analyzed all the moves that it made. Were all these the right choices? Because I got a big score this time, so I guess most of the things that I did this time around seemed to be good. If it got a low score, well then, some of the stuff that I was doing maybe wasn't worth so much. So it's constantly refining its algorithms, it's constantly refining what it should do when there's a ghost just a few seconds past the power pellet. And eventually it started getting really high scores. And then we have deep learning. Deep learning, wow, that was pretty interesting. And I'm gonna show some really cool examples of that in just a little while. Deep learning is really neat because the whole idea of deep learning is to try and model a computer program kind of how the brain works, how the brain works, with neurons. That's not the only kind of machine learning that uses the concept of neurons, but deep learning especially uses these neurons and all the memories that have resulted from previous learning experiences to try and come up with some intuitive information about the data. Deep learning has some really cool, fun examples that I'll be sharing with you later on in today's session. Now, these different approaches to machine learning are commonly grouped into different classifications, or different applications, I should say. Why would you use a particular machine learning approach? What is it commonly used for? One very common application is classification. Classification of content. News topics, for example. Clustering of information, not necessarily into topics, because numerical information doesn't really seem to classify the topics really well, but more like clustering the data that seems similar to other data. Now, this can be helpful for all sorts of statistical analyses, and we'll talk in a little while about what some examples of clustering. Regression. Regression is the word used to describe what most people think of for machine learning, and that's basically getting to the answer given a bunch of variables. So given all these variables, how can I possibly reduce this to the simplest function possible to get down to the final answer? And dimensionality reduction. If you have all this data about sales prices in your home, in your neighborhood, of the homes in your neighborhood, how do you know which one of those features is important? How are you supposed to know? Can you guess? I mean, you could guess. You might be right, you might be wrong. With dimensionality reduction, the computer can try and figure out which of these bits of information really seem to be the most relevant. Which of these bits of information are the important ones? Because the more the computer has to think about when performing predictions of any kind, the slower it's going to be. Especially when you get into neural networks and deep learning and stuff like that, where it has to think about the same thing over and over and over again. If you're giving it a bunch of extra bits of information that it has to ponder, well, that's going to go really slow. Dimensionality reduction can help you narrow down the bits of information that are actually relevant to your purpose, relevant to your goal. Okay, so let's back up a little bit and talk in a little more detail about some of these different approaches to machine learning. Like supervised learning, the first one that I mentioned. Now, for all of these different types of approaches, I'm going to talk about what you give the computer, what it's supposed to learn from it, and what it's supposed to predict, and then I'll follow up with some examples of each. Now, some of these examples will be interesting, I think, especially if you have not had a lot of experience with machine learning, or you're not quite sure how, for example, a retail store knows which coupons to send you, or if you've ever had one of those moments where Facebook seems to have done something really creepy and spooky, showing you an ad for something you were just talking about yesterday, for example, well, then some of these examples that I'll have to show you are pretty interesting. So what's supervised learning in more detail? So if you give a supervised learning algorithm the answer to the question that you have to ask, maybe that's a label you're trying to give some bits of data, and all of the data used to arrive at that answer. Now, it doesn't have to be numbers. Even though I say here it's usually expressed as vectors, and a vector is a line between 2 points, right? A vector is just a representation of numbers. So even if you have words, even if you have letters, even if you have images, they can all be distilled down into numbers, into vectors, and that's something that the machine learning programs that you might use, the machine learning frameworks you might use, actually handle that process for you. So given these variables, all the information about the homes for sale, and a label that's known for these variables, how much the house sold for, The computer has to learn what function can it apply to those vectors to arrive at the results you've already given it. And once it learns what function seems to work really well to those particular vectors to help come up with the answers that you've already given it, well, then it has to make a prediction. Now it has to prove its worth to you. Okay, computer, here's some new data. Use whatever function you figured out and make me a prediction. Now, how close that prediction is to reality is up to the future to find out, right? And if you find out that the computer has done a poor job of predicting, well, there's probably a fault somewhere in the functions that it came up with. Either it needed more data to come to an appropriate conclusion, or perhaps it was too good at figuring out what was needed to come to the answers you had already given it. And any new data, if it's too different from what it had already learned about, just seems like noise to it. You can imagine just looking at the screen that there's a sort of a magic that you have to understand, the person giving data to some machine learning system. There's a sort of a magic that you have to perform to make sure, as the computer is learning, it's not overfitting. That's what they call it, overfitting, and where it's analyzing precisely what it needs to get from precisely your data to precisely your answer, and not actually learning anything, but just drawing lines on a graph somewhere that it will only be able to reuse if your new data happens to line up with those same lines. So there's some magic involved in our own side, and we'll talk about that too. I'm going to give I'm going to actually take you through an experience here of a supervised learning example in just a few minutes. So how about some examples that you might be familiar with in the real world for supervised learning? Here's one that I'm sure a lot of you are familiar with: spam filters. Spam filters are used in a lot of email programs you're familiar with. Maybe you have them at work, and they kind of bug you because perfectly valid emails end up in spam. Or maybe you're using Google Apps, Gmail, or Google Apps for Business, and depending on it, spam filter. So how did that come to be? How do those spam filters actually work? And what is that an example of? In terms of the product of some machine learning? This is an example of a classification exercise. So with all these different machine learning approaches, we have to figure out what we're going to give it, what is it supposed to learn, and what do we expect it to predict in the future. Spam filters, as one of the most common examples I think that most of us have experienced in our lives, they're given in advance when they were taught. They were given a bunch of emails in the form of text. And for each email, they were given a label of spam or not spam. Now, most spam filters, originally, were given no more than just the text of the email. They weren't given information about the sender or the recipient or the time of day or anything like that. But that component analysis we talked about before, where dimensionality reduction, that might actually be a great place for a spam filter to improve if it can learn what parts of the other bits of email metadata might be relevant. But the most common kind of spam filter, when they were first introduced, was just given the text of the email and then a label that a human assigned to it. This is spam or this is not spam. You can imagine being that person. Yeah, this is spam. Clearly, yeah, this is selling Viagra spelled with a 1 in the middle of it. That's got to be spam. Oh, to refinance your home mortgage. Now I can afford all that herbal Viagra that I got in the previous spam. Now that one's spam too. Okay, so every time they saw an email, they had to tag it as spam or not spam. And eventually they had enough data that they could feed it into some program. And the program had to learn on its own what functions can be applied to the text when it is reduced to numeric information. Now see, right there, that's where people kind of get lost on the whole thing. Okay, just before, Dustin, you were talking about home prices. That's clearly numeric information. How can text show up as numbers? I'll tell you how. A little later on in this session, but I'll tell you how. Text can turn into numbers, and I'm not talking, my fellow super nerds out there, I'm not talking about the ASCII table where, capital A is, now see, I said that out loud, now I forgot what capital A, let's say space is 32, capital A 65 or something like that. I'm not talking about that. I mean, the actual word is turned into a number, and the word's relationship to other words is turned into another number, which becomes a vector. And you could do some really cool things when you transform words into vectors like that. And we'll talk about that in a little while. It's pretty neat. So once it's been reduced to this numeric information, can the computer learn what patterns of numbers, what vectors, what numeric sequences or other functions or patterns? What is it that it can figure out? What calculation can it perform on a given body of text that will properly classify it as spam or not spam, given what the human has already told the computer is spam or not spam? And once it's figured all that out, that's the learning or training phase, well, then you can test it and see if it makes the right kinds of predictions. If I give the classification system a new email message and tell it this is spam or not spam, well, then it applies the function that it figured out, that it intuited from the data that you already had fed into it to see if that message is actually spam. Sometimes it's right, sometimes it's not. It seems, to us humans, computers tend to get that wrong. That's what it seems like sometimes. But we have to be careful, and this is why machine learning can be such a great thing. We humans are prone to be biased in certain ways. And one kind of bias that we humans have is confirmation bias. When something confirms our hypothesis, no matter how faulty that hypothesis might be, it tends to confirm to us that our hypothesis was true. You might have seen this in your own lives. If you just bought a car, say you just bought, I don't know, I'm not going to make any assumptions about what kind of car you like, so I'm just going to say you bought a blue car. That's not getting into make and model kind of political discussion. You just bought a blue car, okay? You bought a blue car, and suddenly it seems like there are blue cars freaking everywhere. Well, that's a confirmation bias. There are no more blue cars than there were the day before you just bought your blue car. It just seems like there are because they're standing out to you. And your hypothesis that there's more blue cars is only confirmed every time you see a blue car. Well, computers don't have that kind of bias. In reality, the spam filters that are used right now for your email, especially if you're on like Gmail or Windows Live Mail, their spam filters have gone well beyond the original form, this purely statistical kind of filtering, and they've gone into deep learning and neural networks to come up with their spam filters. They're actually really good. And you, the human reading your email, actually help it by marking an email message as not spam when it's sitting in your spam box. Or even when you delete a message without reading much of it, that might, if it notices a trend there that you always delete messages that have the word Viagra spelled out in them, for example, then it's probably going to start to figure out that that word might be an important signal that it's a spam message, if you're not even reading the message. Those spam filters can get pretty creative. But originally, the first kind was truly supervised and used purely statistical information. The first kind of spam filter was called a Bayesian spam filter, which followed a particular kind of theory of statistics called the Bayesian theory, Bayesian theorem, and Will theorem. Excuse me. We can talk about that a little bit later on as well, if that's something that's of interest to folks. But let's look on to another example: handwriting recognition. Now, this might not seem like it happens in your life very much, but it does if you ever address a letter on an envelope and put it in the mailbox. Handwriting recognition is going on there. When it gets to large sorting machines. They're computer systems that analyze the letter forms that you've written, and as long as they're generally in the right place on the envelope, which is why we're taught as kids where to write that stuff. This is an example of a kind of learning that ends up doing what's called clustering. And by clustering, I mean it takes things that seem kind of similar and groups them together as though they really mean the same thing. And anytime you're analyzing handwriting for letter forms or number forms, for example, you're really clustering all the possible variations of the number 4. Say, if it's generally in the vicinity, if a new picture of a digit is in the vicinity of these other ones, and these other ones I've already classified as being a number 4, well then this one's probably a number 4 as well. And there's a classic machine learning exercise using a database provided by the U.S. government that's actually used to train how to recognize handwritten digits. Or maybe you've seen some more fancy versions of that. There's an app out there called Photomath, which really blew people's minds when it first came out. You could use the camera on your phone to point at a chalkboard or a piece of paper with some formula written on it, and it would give you the answer. Or graph it, or whatever. And that's because it could recognize the handwriting. It clustered each individual digit that was written into some group number 0, group for number 1, group for number 2. And clustering can be helpful for all sorts of problems with machine learning, but handwriting recognition is a very common one. So with this kind of machine learning, we have to remember, like all the others, we have to give it something, we have to figure out what it's supposed to learn from it, and then in order to test, we ask it to make a prediction. So given handwriting samples in the form of small little images, and a human label for each one, the correct interpretation. This is a number 1, this is a number 2, this is a letter Z. That's what we feed into it. And then the computer has to try and figure out. All right. I have 117 different pictures of what the human in front of me has said is a number 4. What can I learn about these pictures that make them more likely to be a number 4 than all those other pictures that I have of the number 9? And that's its job. That's what clustering does. As a form of supervised learning, given those tags of the known images, clustering will figure out what those images for a given label seem to have in common. Now that clustering could be how many of the pixels of the image have been darkened. In other words, how dense is the graphic, how darkened are the letters, how many pixels are taken up by the letter form. There are more pixels taken up by the number 8 than there are by the number 1, for example. So it learns not just how many pixels it takes up or what percentage, but it starts to figure out things like edges. How many sharp edges are in this letter form? How many rounded lines are in this letter form? What are the typical angles of the straight lines in this letter form? And it tries to figure all those things out until finally it comes up with, okay, I think I got it. I think I know how to predict based on the numeric information that I convert that graphic down into. I think I can predict now what letter or number was written. And then you give it a test. You give it a new handwriting sample, one that has not already been labeled with the correct answer, to see if it gets it right. And you might notice the pattern here. With supervised learning, you give it the answers to all these questions, and then you always test to see how well it's doing. And if you're not testing, well, then you're not really evaluating if your model, if your neural network or whatever kind of process algorithm is being used to do the supervised learning. You're not really figuring out if it's good. You're not finding out if it's good. And that's, again, where a little bit of magic comes in for you as the human to figure out how much data should I give it during this training procedure, and how much of it should I hold back for the test to make sure it's good. So it's very common, especially when you get to this kind of exercise where you're doing clustering of images, any kind of recognition of noisy information. Frequently, even though you might have 5,000 samples of digits numbered 0 through 9, all of them labeled with the correct answer, maybe during the training you only give it 700 of them. and then you test with a random 300 to see if it predicted correctly. Maybe you give it 4,000 and you hold back the other 1,000 and just test with those to see how it does. Maybe it's a form of semi-supervised learning where you give it all of it, but you randomly tell it what the correct answer is to some of them. And that correct answer, or I should say, which digits are given the correct answer, maybe that gets randomized every time you train. So there's a lot of human involvement that has to go into creating these learning algorithms. There is no easy button for these, in most cases. At least not for the person coming up with the network. It's possible there's an easy button for you if somebody else already trained a network for you or trained some algorithm for you. So another example, speech recognition. How many phones are going to light up if I say out loud, "Okay, Google, hey, Siri, hey, Cortana"? I don't know how many of your phones just lit up when I did that, but that's a great example of another kind of clustering and supervised learning used for speech recognition. And the same approach is taken for that we use for image recognition. It's given some digital file, a speech sample. Usually these are broken up into words, into individual words, where some other algorithm maybe chopped it at silences, for example, to make sure that they're individual words. And some human has labeled these individual words with the correct sentence, or the correct transcription, the correct word that it transcribes to. So then the computer evaluates the audio. Now, does it hear anything? No, it doesn't. It can't hear anything. Your computer doesn't have ears. Even if it has a microphone, it doesn't have ears. That's something entirely different. So what does it learn from? It learns from the mathematical or numeric representation of that audio file. I mean, it is a file stored on a hard drive, after all. It's made up of zeros and ones, which translate into larger numbers. So it applies some function to the numeric information that represents that file. That numeric information in case of a file of audio might be the range of frequencies that are used, which could be used if you're, it could be useful if you have a training data that consists of both male and female speakers or speakers of different ages. That frequency might be an important bit of information for the computer to not only come up with the correct word, but know if it's a male or female or a child speaker, for example. The numbers that it reduces that audio to might also include something called formants, which are representations of the phonemic sounds that are being made. Maybe you've seen the pronunciation guide on Wikipedia, that strange collection of characters that's printed. That's another example of pronunciation that's been distilled to a series of symbols, and that's something that a computer can do when it evaluates the frequency of audio, of speech, the changes in frequency from one to the next, the visual shape of a graph of those frequencies. It can learn from all these things and eventually come up with some formulas that can be used to predict the proper result. Now these days, this sort of example is done using a very complicated kind of supervised, well, originally supervised learning, and later semi-supervised, that uses a neural network to try and figure out what parts of the audio are relevant. And they get better all the time. Siri, Cortana, Google Now, I should say, Alexa, and the Amazon Echo, they all get better over time. And in order for them to get better over time, they need a constant influx of new data, something you might not be aware of. All those services I just listed off for you keep on their services, on their servers, a copy of the sound file of you speaking. You can actually go into your Google, just Google search for Google Takeout, and that's where their collection is of all the data they have on you. Another on Amazon Alexa or Amazon Echo, right there in the Alexa app. There's a card that's printed out for everything that you've uttered to it, and you can play back the audio recording of that thing that you uttered, which is great fun to find out if your kids have been saying anything that's questionable when you're not in their room. Or it could also be creepy, depending on how you look at it. And they do this because sometimes they'll learn over time how to better predict what it is that you're actually saying, how to better adjust the formulas that it uses to determine how to convert speech into text. Pardon me. Here's another example. Sentiment analysis. This is actually a really helpful one. Sentiment analysis. And I'll give you an example of where this can be helpful for you in the real world, by the way. How many of you, there's no need to respond, it's a rhetorical question, I know we've all been there, but I know a lot of us have been on the phone with some automated voice attendant system, and you've got to press 1 to do this, and press 7 to do that, and press 9 to do this other thing, and if you'd like to hold, press 4 for the... That's, okay, who wants to hold and actually press 4? For those systems like that, by the way, that use speech recognition, what I just had in the previous slide, press or say 1, press or say 2, if you utter an obscenity, perhaps as a gerund that modifies the word operator or agent, like I just want to speak to a beeping agent, there's a good chance that not only are they doing speech-to-text processing to figure out what you're saying, but they've also done some kind of sentiment analysis. And they have scored the profanity that you uttered as a strongly negative sentiment and are more likely to automatically transfer you to an operator. Handy little trick if you got one of those systems that are saying, please say or press 1, just curse at it. Number 1, it's kind of a cathartic feeling. And number 2, it can actually get you to a human faster in some cases. And sentiment analysis plays a part in that. It can. Sentiment analysis can be used to label English text, or any language text really, given a series of information that's already been labeled. A common example of this is movie reviews. Or just reviews in general, like on Yelp. And in fact, Netflix and Yelp have released large bodies of data that researchers and everyday computer hacker programmer types can use to try this sort of thing out. And their data consists of the text of a review of some kind, usually broken down into sentences, and for more complete kind of systems. But sometimes it's just entire paragraphs of data, and then a sentiment score. The sentiment is either is on a scale between -1 to +1. Usually, computers really like only going as far as 1 or -1. By the way, so they score it from -1 to +1. -1 being strongly negative sentiment, +1 being a strongly positive sentiment, and oftentimes they have another score that goes with it, which is it's almost like a confidence, but another kind of number they give is polarity. In other words, how polarizing is this particular sentence? I might say that it's kind of positive, but if it's a polarizing sentence, well then it should be taken with a little bit of extra weight, because it's this one sentence in a grouping of sentences might actually affect the positivity of the other ones, even though it doesn't seem like it's that positive in and of itself. So there's all sorts of variables that can go into it, but the basic, simplest kind of sentiment analysis is this negative or positive? Literally and figuratively. Is it negative or -1, or +1, some range therein? And given those labels for all the text in advance, sentiment analysis will learn what functions it has to apply to the words that are used in that sentence, and the sentences, the phrases, the word pairs, to arrive at the same sentiment score it was told to be true. And eventually, after given enough information, it can learn to predict that very thing. If you give it a sentence, it can predict to you how likely it is that is a positive or negative sentiment, which is pretty cool. It's pretty cool when you think about this, because social networks are a great source of this kind of signal. And if you are Big Corp Inc., and you are interested to find out how people are feeling about your brand, You might be using Twitter's API to get a copy of any tweet that mentions your brand and then perform sentiment analysis on that to see if they're tweeting about you in a positive or negative way. Have you ever wondered why it is when somebody tweets some rant about how much Comcast sucks, they get a response from @ComcastCares pretty quickly? Not only is the @ComcastCares account automatically looking, of course, for mentions of its handle on Twitter, but it's also evaluating the sentiment of those tweets. Now, that body of text, I talked about how sentences and words and things like that are used to calculate sentiment. One of the newer developments in that whole sentiment analysis is the inclusion of emoji. Very commonly, emoji can give you an additional bit of information, additional metric that can be used to indicate sentimentality of a sentence. If it has a smiley face, well then, there's a good chance that that correlates to positive sentiment. Not necessarily always, but a good chance that it does. And if there are lots of smiley faces in the body that you're training with, and you've labeled them all as happy, well, the computer will figure out, okay, well, one of the things all these happy things have in common is they all have smiley face emoji. One of the things all these negative ones have in common is the rage face emoji, or the pile of poo. Either way, it starts to associate that image of the emoji by way of its numerical representation with a particular sentiment, which is pretty cool too. Now, here's one last example of supervised learning and where you might have seen it in your life. One that I think is going to be near and dear to a lot of folks, especially if they think about SharePoint. Not necessarily marketing analytics and prediction for SharePoint, but just in general, analytics and prediction. Now, these are examples of two different kinds of outputs or applications of machine learning. One is regression. Regression is, again, when you distill the knowledge using a function that arrives at an answer. So you take all the variables, you perform some math, and come to a single distinct answer at the other end of it. Like the sale of a home, the home price. And dimensionality reduction. Which of the variables are actually relevant to coming up with a proper answer? That's another example application that this kind of machine learning would do. Marketing analytics. I have a story about this one. So let's say you are the data scientist head at a major retail company. And you have a bunch of data that you already have, and you're going to feed it in to some supervised learning algorithm because there's a label that you've already given to this data. You want to know how well you can predict that label in the future. So you give the purchase history and demographic information, when and where purchases were made, what neighborhood was the purchase made in, as well as some final label like big ticket buyer or buyer likely to be in the second trimester of their pregnancy. Whatever label it is you want to predict. And that one might seem a little weird, but just hang on. So the computer is then tasked to learn based on all this information, all this data you fed into it. Can it come up with a formula that reduces it all down to arrive at the label that you've just given it for all that data? And then make a prediction from some new customer that walks in the door and they start purchasing things. Is there anything about the purchase data that it can use to predict how far along in the pregnancy that buyer is, or how likely are they to be a big ticket buyer soon? Now, the story that goes along with this particular example of a man who was very irate with Target because his daughter, his teenage unwed daughter, started receiving circulars, flyers in the mail from Target, and included in these flyers were coupons and advertisements for baby products. Diapers for infants from 0 to 3 months in the range, right? Layette clothing, cribs, house safe, baby proofing, house safety. And this guy got really upset that his daughter would be receiving these ads and his own he and his wife, they also received these Target circulars in their mail, and theirs didn't have this insert. So he wanted to know who was responsible for this and who entered in some bad data suggesting that his daughter was pregnant. And then a few months later, so the story goes, and it's an apocryphal story. It's various outlets have proven it to be not true. Others have said it is true, but only partially true. Some details have been obscured, blah, blah, blah. I'm here to tell you that it's generally, in a general sense, this is very true. The details may not be, but the experience certainly is true. And he called Target, and he was really upset about this. And a few months later, he has a frank conversation with his daughter. She's pregnant. She was pregnant a few months ago when Dad noticed that she was getting flyers for diapers and things like that in the mail. How could this be? Because Target has access to all sorts of information that go well beyond your purchases, that goes into, yes, indeed, sometimes even medical information. And really, they can use classification and clustering to cluster together purchasers based on their purchase history. And that creates groups of purchasers called cohorts. And then they try to analyze, okay, the computer has grouped all these purchases together. Why has it grouped these purchasers together? Well, as it turns out, there were one of those cohorts would follow a sequence of items that they would buy over the course of a year. And it might be at some point in the start of the sequence, they would buy certain vitamin or mineral supplements, maybe to increase folic acid, let's say. Maybe they changed their laundry detergent brand to something that didn't contain dyes or fragrances. Maybe in the same store, a few months later, they bought paint. Just enough to paint a small room. Maybe they bought a crib. That would be a really heavy sign, a really obvious sign, right? There's like flashing neon sign for that one. So using this history and all these variables, and yeah, they actually went down. Retailers can and do go down to the color of paint and the quantity that you buy. Not only is Target, specifically, this is a known ability of theirs. Target, not only are they 90% or more successful at predicting if a shopper is pregnant, but oftentimes do just as good of a job as their doctor in specifying the week that they will be due, based solely on their purchase information from the store. And I shouldn't say solely, because they do have some other demographic information that you didn't necessarily volunteer. It's just something that they've gotten themselves from maybe your credit report or some anonymized information that's provided by credit card companies. But with all that data, they can actually nail down to the week when a shopper is due. And there's a great article out there about this where the head's data scientist talked about the meetings that he had, where he had to actually had to sit down and have meetings to discuss how creepy a given advertisement might be seen by the recipient. And they wanted to make sure not to wander too far into super creepy territory. These things happen. Home Depot knows if you came into their store and you were in a Lowe's earlier that day, and maybe an Ace the previous week. They know that you did, even if you didn't buy anything. If you left your phone's Wi-Fi and Bluetooth turned on, they're broadcasting their unique IDs. Now, some phones will rotate that unique ID, but only in certain circumstances. So you broadcast your unique ID. Why do you think they both advertise free Wi-Fi in their stores? So you turn on your Wi-Fi and you're thinking, they're just giving me free Wi-Fi so I can showroom. You know, showrooming when you just look at something on a store shelf and then immediately open up your phone and go to Amazon.com. And what did you just do? You just gave a signal to the people running the data analytics department at Home Depot. Number one, that you are a comparison shopper. Number two, that their biggest competitor for your business is Amazon.com. And number three, that you want to buy whatever it is that you're looking up on Amazon.com. Crazy, huh? And even if you don't connect to their Wi-Fi, your phone is still broadcasting a unique ID to the access points in the store. You might have heard of trilateration or multilateration. Some people call it triangulating, where you can estimate the location of something based on the signal strength that is broadcasting to different antennas. Well, stores are filled with antennas. They're even at each individual register. And once you go to the register and you check out and swipe your credit card, now this random anonymous person with a random string of numbers on their cell phone is now John Q. Public, or whatever name you have on your credit card. Now they have associated your name with your phone. And with that, they can send ads to your house, especially if you've already subscribed to some of their circulars, or even if you have one of their store cards. Of course, with your store card, then they have your address. They don't have to look it up from any other system. And yes, stores actually do this. This is not tinfoil hat stuff. This is stuff that stores have been doing for a while. Pretty crazy. All right, so all that's been supervised learning. What about unsupervised learning? This is a common way to think of it. And that's kind of how humans work, right? Neurons that fire together, wire together. An unsupervised learning algorithm is not given the answers to anything. It's just given a whole mess of data. And that's the data scientists use the word mess to refer to anything over. No, I'm just kidding. It's just a lot of data. A lot of data could be a relative term, but I'm not talking about just a few thousand. I'm talking about at least millions of points of data. So given that mess of data, is there anything that it can use to group those individual components of the data together? Which is really helpful if you want to classify words based on their part of speech, for example, because of how they might appear next to others. If you want to classify transactions on your e-commerce store as either valid or fraudulent, it can help you figure these out. It's an unsupervised learning, especially with classification, is helpful to learn what you don't know about your data. It's hard when you see a lot of data to figure out if there's anything that can be used to correlate one entry to another, and that's exactly what unsupervised learning can do for you. It can help to come up with what makes this data similar to others and what sets it apart from others. So that's what it can learn. It learns what the features are about your data. It learns what the features are, the things that are used to differentiate one line of data from the next, and then groups them all together by what their neighbors are. In fact, the algorithm that's commonly used for this kind of grouping or classification is called nearest neighbor. Now, occasionally you'll find somebody that's a hermit. Somebody doesn't have a nearest neighbor. They would be an outlier, right? It could be, if it was an e-commerce transaction database, that particular transaction might be a fraudulent one. Maybe there are some values that could not be used to put it reliably into one of those existing groups. And this can be helpful, not just for e-commerce. This can be helpful in any kind of intranet situation as well. For example, you might be collecting all kinds of web analytics and not really understanding what questions you want to ask of it. You just want to see if there are any groups that can be determined from this information. An unsupervised learning algorithm might point out to you, might help you discover that there is a collection of people who tend to search all the time from a given page, and they don't click much. So if it created a group like that, out of all of the analytics from your SharePoint sites and the users that are accessing them, you could learn something from that. You could learn, okay, well, there is a site and all of its users tend to, well, first of all, there's a group of users, a cohort collection, that all tend to use search and don't tend to click around on the site. And as you examine what that group might have in common, maybe you do another pass of unsupervised learning over just that particular group of users, the ones that don't click around much and always use search, to see what other groups they might fall into. And maybe you find out that they are all falling into a group of users of a particular site. Well, that's just told you that that site is not very usable. That's just told you that users tend not to click around on that site for whatever reason. Maybe it's ugly. Maybe they don't like the dancing kittens on there, the rainbows and ponies even animating across the header. Who knows why they're not doing it? But for some reason, they're not clicking around. They're searching instead. Maybe there's too much information. It's too dense. That's not something the computer can tell you. The computer can only tell you, these people I grouped together for some reason, and you're going to have to figure out why. And it's not a failure of the unsupervised learning algorithm. That is actually a success of it, to tell you that there was that group of people to begin with. So another example that is used would be topic classification. So if I had a proper mess of news articles, is there something about each news article that can be used to group them together? Topic classification. This is also done frequently in movie reviews and machine learning exercises that are designed to teach you how to do this sort of thing. So machine learning exercises might take you through like reviews on IMDb and collect them together and try to learn if there are topics that are similar. As people tend to say the same sorts of things about the same kinds of movies. So topic classification can be used not just for topics, but to find out what other people have similar interests as well. The types of things that you click on the Facebook news feed can inform Facebook about the topics that you are interested in. And then given those bits of information, now we have to predict. If I give you a new news article, can you tell me what topic it is? And we go back to the semi-supervised learning. That last of the non-neural network sorts of machine learning. I like to call this the help me help you kind of learning. Once again, a whole mess of data is fed into the computer, but some of it has a suggested answer given to it by the human. And the computer has to figure out what data can be grouped together as similar to others. And because you've labeled some of it, its guess on those as it tries to test its own hypotheses to figure out if it's going to be a good model or not, its guess on those can be given a stronger weight. If you've given it the answer, it's going to try its guess to see if it came up with the same answer. And it's helpful to have this combination. It's helpful to have the mass of data that's unlabeled with some small subset of it that is labeled, because the computer can sort of check its work as it goes. That's just one example of how that can be useful. And if, for some reason, it comes up with a model, and then it then gets to a record that you've labeled and its prediction is not true, well, then it can figure out, do I need to update that model? Do I need to update my understanding of it? So what's an example of semi-supervised learning? You are one. You. Not the royal you, but you, the person hearing my voice right now. You are an example of a system that performs semi-supervised learning. Because when you were a child, for example, your parents told you at some point, probably, I don't know, I'm just guessing, that fruit is good for you, poison is bad. Well, I mean, it seems kind of obvious on the face of it, right? But it's not obvious to a child, necessarily, especially when poison comes in really bright, colorful bottles, and fruit just so happens to be bright and colorful as well. So your parents gave you a label on one type of food. Out of all the food that you eat, they've given you a label of one type of food. And somehow you, hopefully most of you, successfully able to differentiate in your head what's poison and what's fruit. You've come up with some mental model for the characteristics that are in common with all fruit. And you've also come up with some mental model of the things that all seem to be similar when it comes to poison. Poison tends to be bitter. Fruit tends to be sweet, for example. Fruit tends to not come in bottles on its own, but some product of the fruit might. And at some point in your childhood, you were given a bottle of liquid. And the photo that was on that bottle of liquid hopefully wasn't a skull and crossbones, because you probably figured out early that's poison. But maybe it's a photo of an apple. So your mind has to predict, is the liquid good for you? Well, you were given partial information about this in the past. you're supposed to learn now in a semi-supervised way. And semi-supervised, once again, means that some of the data you are already told the answer to. So how have people used this sort of thing? How have people used machine learning to figure out something, to answer some question? And I'm going to use a classic example, and one that, granted, one that you'll encounter in other places, but one that is still an excellent example and an excellent, I think, story centering around some kind of machine learning. So I have open on my screen right now a web-based application called a Jupyter Notebook. Jupyter, Jupyter. Jupyter Notebook. It is a web-based development environment, if you will, used by primarily a programming language called Python. Python is one of many programming languages, of course, but it is one of just a handful that are that's commonly used by people performing analysis of any kind of data, scientific analysis or statistical analysis of data. I also have open on my machine, I'm going to drag over into another window here, something that you might be more familiar with, Excel. Believe it or not, Excel is one of the most popular tools in use by data scientists of any kind, anybody doing data analysis, because machine learning, before we can ask machines to make predictions of the things that we want to predict, machine learning has to have good data coming into it. We have to have data coming into it that's meaningful. So what I have here, you might guess from the title of my window, is a list of passengers that were on the Titanic. Not all of them, some of them. Actually, this one in particular, as I scroll through. I mean, make sure I open the right one. This one is indeed not all of them. This is 891 different people and whether or not they survived. There are another group of people whose data I have withheld from my program here, withheld from Excel. Another 400 plus people who I don't want to be involved in my training process. And believe it or not, you can actually start to get an idea for what sorts of questions you might be able to ask and what the shape, and I mean that both literally and figuratively, of your data is by using Excel. A lot of people poo-poo this whole idea from the start, but in reality, a lot of data science starts here in Excel. And the unfortunate side of the whole data science and data modeling and machine learning side is that data is messy. And before you can even get to the fun part of using a computer to make some predictions for you, you have to clean stuff up. Now, there are ways that programming languages like Python or applications like Excel can help make this process go a little faster for you. But we're just going to have a look first at this particular bit of data. Now, right now, it was just imported from a CSV, so I'll turn this into a table here in Excel. And believe it or not, yes, we're doing data science right now. We're going to turn to the machine learning side in just a few minutes, but we're starting on the foundation of it all, which is an analysis and data science. So I'm going to convert this into a table. Excel pops up. Are you sure you want to do this? This is where the data is going to be. Yes, I'm sure I want to do that. So off you go. Now it's made a table of my data, which is super handy. It's super handy because you can then do some analysis on your own right here. For example, you can sort by their age. Just to see if I sort by, let's get another click going in there. There we go. If I sort by their age, Hello, how about you let me click, Excel? That's okay. We'll take the other approach to sort by the age. I'm going to sort. Okay. One more time. I'm going to select my table. That's a fun thing for Excel to do for me. And I'm going, there's a filter applied, and I'm going to take that off. Turn the filters back on. Sort. There we go. I'm going to sort by the age. Let's do largest to smallest. Now you'll notice that this data is not very clean. First of all, we have one person, at least one, with a decimal in their age. I mean, we know what that means, that they're halfway between 70 and 71 years, but here's another one, 55.5. Seems to be the men that do that. I don't know what's up with that. 45 and a half, both men. 40.5, you got it. Men seem really insecure about... See, these people here, these men didn't want to admit that they were in their 40s. Because once they turn 41, they're in their 40s. At 40, they're just 40. 41, well, now I'm in my 40s. Nobody wants to admit that. And I'll see if I can make this font a little larger here in Excel, by the way. So I realize it might be a little... YouTube's encoding might make this a little harder to read. So we'll make this text a little larger. And then we have a bunch of others in our data set, well, that don't have an age specified. Well, that's going to make things a little problematic for us, I think, if we are trying to make predictions about whether or not somebody survived on the Titanic, and we expect the age might be a part of that prediction process. Well, I probably want to know what their age is. Which means that if we can't find a way to come up with their age, their data really can't be used to make predictions based on somebody's age. We can't train a neural network using age as a feature, train any machine learning algorithm, I should say, on age as a feature if we don't have an age specified for each one of our passengers. So what else do we have here? We have the class cabin that they were in, whether or not this person survived, their name and gender. Did they have siblings with them? What was their ticket number? How much did they pay for it? What cabin are they in? Where did they embark? Where did they get on board? Then maybe that's relevant. So this person right here, no sibling or spouse, but they do have one parent or child on board with them. Given that this person is 2 years old, do you think it's a parent on board or a child on board? That's probably a parent. So here's another opportunity for us to clean up this data even more. We can make a guess ourselves to give the computer more relevant information, not just do they have parents or children with them, are they themselves likely to be the parent or the child? Maybe we can group by people with with the same last name who embarked at the same location, and then sort them by age. If they have a spouse with them, and they're over a certain age, there are other people that share the same name and the same ticket class. Well, maybe those folks are all in a family, and the older ones are the parents and the younger ones are the children. Because whether or not they had a family on board with them, that might factor into their survival as well. We don't know. This is the point of the beginning of any of this machine learning kind of analysis, whether you're doing an analysis of analytics or you're doing an analysis of the passenger manifest from the Titanic. So what do you always hear about big boat wrecks like this or other accidents that happen on the ocean? With a phrase that you always hear, save the women and children, right? The women and children first. What do you think? You think women and children made it off or more likely to survive? Let's see. whenever I'm going to analyze any data in Excel, and the whole clicking up in the top is really kind of, oh, hold on, I've got this dialog that's showing up. That's just showing up off the screen, so I was actually doing what I was asking it to do. It just wasn't appearing on the screen. There we go. So whenever I'm going to start my exploration of this analysis, pivot tables are the way to go, man. I mean, anybody that uses Excel during their day-to-day work will tell you that that's where a lot of the power in Excel lies, right? And it might not seem very sexy to use Excel to do this sort of thing, but a lot of analysis can be done here. And it's not machine learning yet, but we can use some of the intuitions that we learn from Excel to inform how we might write an algorithm to perform machine learning later on. So with my table selected, I'm going to go ahead and make a pivot table. Now I'll place it on a new worksheet inside this workbook, so it just shows up as another tab. And there's my new pivot table. Let's see. I want to get just a few bits of information from this grouping of people. I want to grab, well, let's find out the gender. Let's see if women and children really were the ones to survive. So let's grab the gender. Okay. And let's also make sure that we label those as separate rows. So now we can see. And I'll make this larger again because I'm sure it's hard to read in YouTube rather. There we go. So I can see how many males we have, how many females we have. That we do have a grand total that is actually the sum of those, and it matches the number of people that we originally thought we had on here. So how about survived? Let's bring survived in here. I'm going to take the gender out for now. We've got survived that I'm going to bring in here twice. The first one is set to be a sum, so we can see in total how many have survived, the sum of summarized, as we can see here. The second column, I'll change this to be a total count for the given gender. So it doesn't matter if survived was 0 or 1, just how many entries at least were known who had survived or not. And I'm just going to update the headings here, say survivors. And the total. And right next to it, we can calculate survivors divided by total number in that particular group. And fill that on down to the next one. How about we fill it on down to the next one by retyping it? Sometimes Excel doesn't give enough data. See, even Excel, if you don't give it enough data. And we can format these as percentages also, if that makes more sense. So, look at that. We've already gotten some insight, I think, into what happened on the Titanic. 75% of the women on the Titanic, at least in this set of data, it's just a sample of it, not all of it, 75% of them survived. 20% of them, 19% of them didn't. Excuse me, 19% of the men survived. 26% of the females didn't. It's a good thing the computer's doing the math for me. Oh, well, I mean, that's pretty interesting. So this we might think of using this as one of the more prominent features in our model to figure out, okay, did the women all, is it more likely that you survive because you're a woman? But what we've done also is given us a weight at least for this one variable. And we, the human, did. A computer didn't figure it out. We, the humans, figured out, okay, well, in terms of survivability, it appears so far that your gender, if you're a male, should be given a certain weight to your survivability. And if you're female, well, then that should be given a higher weight to your survivability, because 74% of females survived, but only 19% of the males survived. Maybe that's not enough, really. Is that enough data? Is that enough data for us to create a kind of machine learning model? Is it that simple? Just gender? I wouldn't think it's that simple. So we can look at the rest of our data set, and I'll open up the other half of our data set that we can use to test. Then I'll make this larger as well. And we'll do the same thing. I'll make this into a table at the top. And I'm going to summarize this with a pivot table. And make this a little larger for us to see. Now, we don't know how many of these survived yet. We're going to have to make our prediction, because our test data doesn't have the answers for us. So what's our prediction? We have to come up with our own prediction that says, if you're female, well, the likelihood of you surviving is going to be about 75%. And we'll just say, if you're a male, the likelihood of surviving is about 19%. We'll add a new column. Oh, excuse me, table. I'm just going to add a new column by right-clicking, actually. I'm going to add a new column into our table. We'll call it survived. We have gender. So we can ask if their gender is equal to male. Let's simplify this even more. I realized that I'm taking up more time than I originally rehearsed for this part of the session. So let's just say all the men died, just to see how close we get for that. I know some of you might be saying that's a little rough, Dustin. Let's say if you're male, you died. If you're female, you didn't. So we'll just fill that on down. And look, all the women survived and all the men didn't. If we have female is that much of a weight and that much of a winning factor for your survivability, then let's really test that hypothesis out. We would ask a machine learning algorithm at this point, given what it knows about the gender, and if we say they have survived or not in our original set of data, and it makes its predictions, will its predictions line up with the truth of the matter? This very basic prediction, if you're a woman, you survived, if you're a man, you didn't, won't line up to the truth, because this says that all the women survived and all the men didn't. So at some point, Excel is going to exceed its abilities for us. And we can add some more math to this if we wanted to. That's actually what I would otherwise be spending more time on, but I'm coming up toward the latter part of my session. I want to make sure to have some time for Q&A. So I won't continue to model my prediction in Excel. I'll get on to the whole machine learning part of it, and let's get Python involved in the process. Pardon me. Now, Python, as I said, one of the many programming languages out there, but the one that tends to be preferred by data scientists or anybody that just wants to wrangle data for a living, or even just explore data. You can think of some parts of what I'm going to show you as Python as a super version of Excel for programmers. Now, one thing that I like to do in Python in particular is to figure out what my data kind of looks like. What does my data sort of look like? What's the structure of my information? So the first thing that I like to do myself is bring in a Python package that is optimized for managing tables of information, just like you would make a table in Excel. And I'm going to make my fonts here larger as well, so that it really shows up in the screen share. And the package in Python that does an excellent job for manipulating tables of information is called pandas. Pandas, depending on who you ask. I like to say pandas because I imagine cute little pandas all with calculators in their hand for some reason. I don't know why. So I'm going to import that package into my Jupyter notebook. Jupyter notebooks are really great when you're learning Python also. For those of you that are just too stuck in the .NET world, which certainly has its own machine learning capabilities as well, that you have not had a chance to explore Python and you're afraid that it would just be too involved and take too much time. Tools like Jupyter Notebook make it really nice to learn Python. I started working with Python myself just maybe 5 years ago. And that was without really using notebooks, this whole Jupyter thing. I started using Jupyter Notebooks about 2 years ago. They were called IPython notebooks back then. And man, what a difference it's made. And I'll show you why in just a moment. You'll really see why. I'm going to import this pandas library as PD. There's another library that's really helpful for doing a lot of mathematical functions. It's sort of the algebraic library of Python because it has heavily optimized routines for working with large sets of numbers in both arrays, which are lists, and matrices, sort of like grids, even multiple dimensions of matrices. And that's NumPy, or NumPy as some people say, but NumPy, numbers for Python. It's common to give these things aliases so you're not typing those words all the time, which is just what I've done there. I've given it an alias. Now, as soon as I hit on my machine Option Enter, it would be something probably like Alt Enter on PC, on Windows. It runs, the notebook runs that code. That code has been run, and any result from that is now available to me in any other cell of my notebook, which is pretty cool. This is taking another version of the console that you're just using a read, evaluate, process, loop, the REPL console, just using like the node console or something. It takes it to another level to have to have each cell separate like this and have code running from one line to the next. Now, those of you that are, again, sort of new to Python, there are multiple options for learning the programming language itself. For learning more about its applicability to machine learning, of course, there are online options. I will be running myself a SharePoint-specific course that will give you a crash course in machine learning and SharePoint and Python in particular. And that course that I have coming up will send out a notice to those of you that have subscribed to see us live, and I'll also be updating the description and comment section of the live feed here, or the archive of the live feed here today, with a link to it as well. It's my SharePoint data mining and machine learning class. It's really designed to be as little of an intrusive factor of your day as possible. We meet in that class once a week on Mondays, and then again once a week on Fridays for live instruction. The rest of it is spent and your free time, your copious free time each week performing exercises as sort of a distance learning college type approach, where the term for that particular class is 8 weeks, and lots of stuff covered in those 8 weeks. So there are definitely lots of options for you if you're interested in diving into Python even more than you'll see during this demonstration today. So I'm going to read in now into Python, since I have the libraries necessary to process data in some kind of table form. I'm going to read in a table of information. Now, tables in Python, and it's the same with other statistical analysis type languages like R or MATLAB, are also often called data frames. So that's where I use the abbreviation DF. And I'm going to ask pandas, that PD library that we have, to do me the favor of reading a CSV file. And I already have one stored on my computer. Now, my CSV file, I want to have it ignore the first line of it. So I'm going to tell it that the first line is a header, so I don't want it to try and actually read that data. And once I do that, oops, hold on, I have that in the wrong, I put that in the wrong spot. Give me just a second. That should actually be in, that's Titanic, that's what I call this file, not train. Titanic. There we go. And see, immediate evaluation of my error message too. But let's see what the data looks like. So if I execute that, I can see a table of my data. I can see that sometimes the cabin has information, sometimes it doesn't. That NaN, or not a number, means there wasn't data in there. Same goes with age. There will be some folks with an age without a number. And we can actually use some features that are built in here to the data frame object of pandas to help us find those. Let's just look at the first couple of those. So here are the first three folks. And you can see again, cabin, not a number. Now we can ask for the first or last few parts of it if we wanted to. What type of information is actually stored in here though? Let's see what type of information, what data types are stored in this particular collection of data. Well, there's a passenger ID, it's an integer. Whether or not they survived is an integer. Is that right? Maybe that should be a Boolean, but you know, computers, when doing machine learning, like ones and zeros more than trues and falses. Passenger class, the name is an object. Basically anything that can't be a number of some kind, it comes back as an object. And we can get even more information about those different data types. That tells you information, that just guesses. It guessed about the data types of those things, but it can also tell us if any of them were nulled. In other words, if they have complete information, what fields might be missing information? Well, there are 891 passengers. 714 of them have ages. That's the one with non-null. Only 204 have their cabins known. Well, that could be a little problematic when we're trying to do some machine learning, right? If a cabin, we got to figure out a way to come up with a cabin if we don't have that data. We can also ask pandas to describe mathematically some of the interesting statistics about our particular collection that we have here. Passenger ID, well, we don't really need passenger ID to be summarized in any way, shape, or form, but look at this. This is a total count of how many people, of the people that were in this data set, 891. But because survived is a number, it basically tells us the standard and mean as percentages of who survived. Survived is 1, and didn't survive is 0. Now, how about age? Is this really the mean of age? Well, maybe not so much. We know there's a lot of missing values from there. As it turns out, pandas is pretty smart. If it was missing, it just didn't include it when it was doing that calculation. I can see about half of those were with a sibling or spouse. I can see the average fare paid. Now, as I said, part of this whole process is not just looking at and evaluating the data, but we've got to clean this data up too. We've got to figure out, can we fake any of this data? So for example, we can ask the Python tool, let me just minimize that window, can ask the pandas through our data frame to show us a data frame, but in square brackets I'm going to provide, well, there's some filter that I want you to check for. I don't want to see all of it. I only want to see it if the age that we have stored is empty. So let's see that first. All right, so there's a bunch of people with no age. All right, of all those people with no age, well, let's see what we might actually care about. Let's see and get their gender and their passenger class, and make sure that, again, that their age is truly empty. So when I say this is like Excel for programmers, you can see I really mean just that. It's letting us, as programmers, letting me, as the programmer in this case, type in code that essentially produces a subset of an Excel spreadsheet. In fact, I can take any one of these filtered versions that I create and save it literally as an Excel file. Well, there are a few other things that we're going to do to examine this information. First, let's see visually by importing a graphing function, a graphing library, I should say, in Python. Let's see more visually how our age distribution goes. Now, I just set up the new environment for this. I wanted to make sure that that PyLab, which is one of the packages for graphing that I'm going to be using, is actually visible here, and it hasn't been imported, so that's good. So what I'm going to do is take this data frame and get the ages of all my passengers, and let's get a histogram of that data and show that as a new window. And here's my window. Here's a histogram of my passengers by their age. So this is binning. There's another term for this that folks have used, binning. I'm binning my passengers together by their age. Now we can be very specific about how those are binned right now. It's binned, you can see by the numbers at the bottom, by every 10 years. And maybe that's not relevant. There's also a lot of people that actually don't have ages, and we don't necessarily want to have those plotted on the screen either. So what we can do is kind of chain together another set of requests first, drop not applicable or not a number. We can drop those out of our data set, and we can change how many bins it's going to group people into. Maybe we only want it to group it into, maybe we want to group it into 20 different bins of people, ranging in age from 0 to, I don't know how old was the oldest person. We can go back in Excel real quick. I think I had that as one of my, I think I was still sorting as that in the Titanic set. Now let's look at Titanic. Not still sorting, but I'll go ahead and resort by that age to make sure that I am seeing the oldest person. I would do that in descending order. 80, yeah, well, not too old. So from 0 to 80, and we can put all those together. And again, this is just popped up and, well, let's see if it'll pop it open again. It has the asterisk on there, like it's still trying to run it, so I might have might be having a technical issue with that, running that graph again. So what I'm going to do is actually tell this to restart its process and then just rerun everything from the beginning. So the should all be restarted. And oh, I had a typo in there. That's what was wrong. So I have my bins and my range. Non-keyword arg after keyword arg. Oh, I need to specify, I think, the alpha transparency of that. No, see, that's just going to give me some grief. So let's just get the histogram without specifying the age entirely up to 80. Just disappeared on me. Do that again. Come on, come back. And that's where it restarted on me. My apologies for that. Let's go ahead and rerun that one last time. Run all, and my graphic pops up. Figure 1, there it is. Now using 20 different bins of data. And look, it just disappeared again. I think between the rehearsal and now, the only thing that's changed is the software that's being used to broadcast it, and that must be doing something weird with the cell that normally pops up with the graphics, because you see the asterisk, that means that it still thinks it's running, but I can't actually switch to that particular window anymore for some reason. It doesn't actually open it any longer, and that might be the broadcast software that's interfering with that. So I'll make sure to close it before I come in from the top again. So I'm going to restart my kernel and run all, and pop it up one last time. My graphic. And before it gives me grief, I'll close it, and see, now the asterisk went away. Good, that's good. So we have gender as gender here as a word in the original data. It was male or female, right? Gender, well, male and female, that's not something that we can actually use very well as when we're trying to do math on things. And as I said, one of the things that computers really like for us to do is convert words of any kind into numbers. So we can actually create a function in Python to do just that. We create a very quick, some people call it an anonymous function. In Python, it's called a lambda. So I can ask my data frame to create a new column. I'm going to call it gender, and I will set it equal to, and then I'm going to do a function on that sex column that's already there. And say that for every one of those entries that you have for sex, first let's get the, well, actually, let's go ahead and map it directly to. Let's map it to a binary, because in this case the information that we have in gender is binary. So if it's female, that'll be 0, and if it's male, which is just that way because it's in alphabetical order. And just to make sure that Pandas understands, this should be an integer that I'm creating here. And if we look at that now, we'll see there's another column called gender, and male is 1 and female is 0. So now we have numbers that we can deal with for each of those things. And I'm looking at my clock and realizing I spent a lot more time on my storytelling in the beginning of this, so I'm going to go a little bit long. And next time we do this webinar, I think I'm just going to extend it, because I don't want to miss out on any of the stuff that I'm showing you guys. I think it's best to maybe make this just a little longer, because we're still preparing our the data for processing, and still haven't gotten to the SharePoint side of things. Actually, I think the best thing to do is to make this a part 2. Now that my rehearsal went a little too fast, I guess, and now that it's done live and on the broadcast, I know I have had to slow the broadcast down a little bit because of the encoding from YouTube. So I think I'm just going to do a part 2 on this, and I'll just carry on until our closing time today. We'll have part 2 in a couple of weeks. That seems like it's even better idea. So then you get 4 hours worth of stuff instead of 2 with a bunch of stuff missing. Seems like a better idea to me anyway. So we have numbers for genders, which is great. Well, what about ages? We have a bunch of people who don't have any ages. So we'll have to figure out a way to process that. I'm sort of setting the stage for what we'll cover in part 2, now that I realize that part 1 doesn't leave me nearly enough time. So in part 2, we're going to be dealing with some of the other data that we have in order to make it easier for the machine learning aspect to actually learn from it. We've already got the gender turned into a number. And with the age, there are a bunch of people whose ages we don't know. So we can make some guesses about that. So we'll have a look at what else can we use to guess the age of somebody. For example, if they have sibling and spouse, but no parent or child, then that's a good chance. If they have no parent or child, that must mean that they have spouse on board, which means they are at least old enough to have been married, so we can make some guesses about their age using that information. How much fare they paid isn't necessarily here for all of them. Neither is the cabin where they are currently staying. However, what we do have is some combination of those things: the fare, the cabin, and where they embarked. So, for example, all these people in S, with I don't want to say Southampton, I think is what S referred to in this particular data set. So they got on at Southampton. If we know that this is their fare, getting on in Southampton, we can find other people that got on in Southampton that paid a similar fare and see what their class is. So we'll find that out during our exploration as well. There are other ways to make these kinds of calculations so that we can clean up our data, and those places in our data where we don't have valid numbers, we're going to customize them so that we are at least dealing with semi-realistic numbers so that we can help the computer along a little bit. This might seem like it's cheating to inject your own data when that data wasn't there to begin with. In reality, data cleansing, this important first step in machine learning, is not just about getting rid of the stuff that isn't going to work. It's also about coming up with appropriate approximations where you have data that is otherwise unavailable. And that means that we have to make sure our approximations, if we were to check them against other data where that data does exist, that our approximations don't seem too wide off the mark. As long as our approximations seem pretty close to what other people have done with the same, what the other data might reflect with the same kind of information, then it's okay to use approximations in a machine learning model. So during part 2, which we'll get some advertisements up for and get an email out for as well, during part 2, we'll be discussing more of using Python, and in particular a machine learning library in Python called SCKit to do the machine learning portion of our presentation. It has a lot of built-in frameworks for, or CIKit, I should say, scikit, built-in frameworks for performing machine learning analyses of data, frameworks that include regression type algorithms, classification type algorithms, principal component analysis, which is like we talked about how some machine learning is designed to identify which features really truly are relevant. We can actually ask the computer to calculate some of that for us using principal component analysis. So there's a lot still to come, and 2 hours wasn't nearly enough, so we're going to split this up into 2 parts. Also to come is the SharePoint side of it, where I'll take you through the process of installing a library that I have extended from an open source library, a special analytics library that I don't want to say written, because the original part of it was actually created in another open source package, so I forked that and expanded on it to turn it into something more native to SharePoint. So some analytical tools that you can run on your SharePoint server to capture data about users' behavior on your SharePoint site and perform the same kind of analysis there, find cohorts, fill in missing data, make predictions to answer questions that we have, just like we're doing with the Titanic data set here. So there's a lot more that we'll have in part 2. I do apologize for having far too much to say in 2 hours. And I'm looking forward to having part 2 with you guys. We'll send out an email once that date has been set in stone. We also have another free webinar coming up. Heather will be doing a free webinar on CSS in SharePoint. The information is actually right in the description there of this particular stream. And that's going to come up on Friday, September 9th. Overview of not just CSS, but in general branding options available for those of you that are using SharePoint Online or Office 365, as some people refer to it. So part 2 of this webinar will come likely after Heather's upcoming free webinar on Friday the 9th. So I'll give it probably 3 weeks then for part 2. And we'll send out a notice to everybody who signed up here in part 1. Thank you so much for spending this time with me. We do have the chat that's open on the side. And I'm going to make sure that I can actually see it, because I was having a hard time originally when I was broadcasting, seeing the actual chat showing up on the side. But now that my slide deck is not broadcasting, I can see it. So I'm going to open the floor up for questions. Let's see. If there are any questions that you have, you can go ahead and pop into the chat. I do see that some folks have chatted as we carried on. Thanks, Celisa. Part 2 is going to have a lot more of a dive into the SharePoint side of things. So hopefully it's given you a good overview of what machine learning really is all about, and you can start to kind of envision. It's not necessarily the most glamorous of experiences when you start, because there's so much of that data cleansing that has to happen, right? Make the data look good for the machine to process. But part 2 has more of the learning part of it, and that's where we also get into the SharePoint side of things. It's funny how rehearsals end up going by a lot faster than the live broadcasts. I am also looking forward to part 2, though. Thanks very much. Any other questions, feel free there in the chat to post them. And I'll leave that up for just a little while longer before that gets closed down. So the analytics, the question is, for the sake of those that won't necessarily see the chat if they're playing back the recording of this, the question is asked, how would the analytics that you built differ from the business intelligence feature of SharePoint? Well, the big thing about this is that the analytics package that I'll have to share with you collects all of its data on the client-side behavior of the actual browsing user. So it's collecting not just what pages they went to, but it's collecting where their cursor moves, what they select on a table on the page, for example, if they resort information on the page, how much time they spend. A lot of people, just as a signal in case it might be useful for some machine learning, a lot of people actually use their cursor as they read something on the screen, right? They kind of move their cursor along as they go. And that's something that is also captured, just in case that might be a relevant signal to your analytics. We also capture, I'll try to be more intelligent about not just capturing what they click on, but give it a name, like click web part title announcements, click sort header announcements, expiration date, that sort of thing. So you can really drill into the things that the server is either unaware of or doesn't log because the work is happening on the client side. So it's analytics that go well beyond just what the server is aware of. The server right now is really not aware of where the person's mouse is moving, for example, or how far down the page they scrolled, or if they tabbed away to a different tab and then came back to SharePoint sometime later. That's another kind of metric that may be valuable to know if you're finding out how useful a particular site is. Do they leave it open as a reference guide and come back to it frequently during the day without reloading it? So you'll be able to answer questions like that by using the analytics that my analytics provides, and it's open source. It's on a private repository that we have now. I had intended originally to make that public when this web seminar was over, but we have a little more to go on this series. So we're going to go part 2, so I'll open that up to the public after part 2 is done. So capturing lots and lots of cool stuff. And those of you that are interested in that kind of analytics outside of SharePoint, I mean, the one that I'm doing is very specific to SharePoint, but there is another library out there called Heap Analytics. I'll also post a link to that. And Heap Analytics does something sort of similar. They've changed their site, so it's not showing the original graphics on there that it used to, but I think the features page might. So on Heap Analytics, you can choose to identify things based on just what I'm doing with my analytics, what they click on, give it a name, and that's pretty much what my analytics will do. But this one is designed for public-facing sites and can collect some other information from folks. This also lets you identify users on public-facing sites. You can pass in some identifier if you know that they've logged in. The version that I have for SharePoint, which is not heap analytics, this is just for those of you interested in public-facing stuff. For my analytics, it assumes they are identified because they've signed in. And if that identification is not enough, it also does scrape the name from the welcome control in SharePoint, whichever version of SharePoint you're using, and uses that to additionally identify a user. So you can tell from there. I do have a sample enrichment script that you can run against Active Directory that will take their name and their login and enrich it with other information that you might have from Active Directory. So you can actually do cohort analysis based on the department of your organization they're from if you have that inside your Active Directory, for example. So there's a lot that you can do with the data that I'll be capturing on this other analytics tool. And those of you running non-SharePoint public-facing sites, Heap Analytics is a really clever analytics system for public-facing sites. The biggest benefit, though, for both Heap and the one that I've done is that it doesn't require you to instrument anything. You don't have to add anything new other than a script tag. Whereas in Google Analytics or something like that, you have to specify, I want to track when these links are clicked. I want to track when this thing is clicked, even though it's not a hyperlink. I want to track how long people are hanging around on the page because a JavaScript event fired off. You have to do all those things manually with Google Analytics, and with mine and with Heap, you don't. It instruments everything. It logs an almost obscene amount of data, but the more data, the better when it comes to machine learning. For it to make predictions on data, it has to have a lot of data to start with. And that was the driving goal behind my own custom analytics for SharePoint, is to collect as much data as possible. And very carefully, gracefully straddle that border of lots of data and so much data it's creepy. So we do keep that in mind. Try not to be creepy. Thanks for asking. Great question. Any last questions before our live stream comes to a close for today? And we'll give folks just another minute because unlike other chat systems, of course, we can't tell if people are typing. So we'll just give you another moment. And otherwise, if there aren't any more that get posted now, I'd like to thank you for spending a couple hours with me. And also, thanks for understanding it. For a very long time, we've focused on multi-day classes. We're returning to our roots of offering some free services as well with this free webinar series. Thank you for your understanding that there's just far too much for us to go into in 2 hours, that our rehearsals were a little faster than the live broadcast. And actually having the second block of 2 hours gives me even a little more time to go into more detail than I had originally intended to when it was rehearsed. So it's going to be an exciting time, I think, when part 2 comes around. I'm really looking forward to it. Thank you all for coming here and joining us today. Once again, my name is Dustin Miller from SharePoint Experts. After this session is done, sometime after at least, the recording will be made available, and we'll send out an email where you can go back and play back that recording. It's maintained as a recording on YouTube, but it is marked as unlisted, so you'll have to look for that email from us to get access to that recording. Thanks so much for coming out to us. We hope to see you on part 2, and once we've got the dates finalized for that, we'll send out a notice to everyone. Thanks again, and we'll see you soon.